So, before today I begin the next part, I'd like to discuss with you a little bit more about, we can say, the Tyndall effect and little bit more about the electrical properties. So that I'll go to the next one because I believe that's something more I have to say you. Now, that is Tyndall effect. What is its importance? Now, let me tell you, Tyndall effect was done by Zsigmond. That is Zsigmond. He devised an instrument called ultra microscope. Let me tell you, and an intense beam of light from a particular lamp. We can say the name of the lamp is what? Arc lamp. Correct. The arc lamp is focused on the colloidal solution, and that colloidal solution you took it in a beaker or in a glass vessel. You can say that you will be taking it, and when it is being focused, you will find it out. If it is a true solution, then the light will pass through. But if it is being colloidal solution, then the light gets scattered. Now how do we come to know? You will observe it under a microscope. You'll observe this effect. Listen carefully. You'll observe this effect under a microscope. You'll observe it. That is, you'll pass the light from the arc lamp into the colloidal solution. You'll observe it, that what is going to happen. The light which is scattered by each individual colloidal particles appears as a bright star against a dark background, because basically this experiment is being done in a dark room. It's a dark room experiment. Thus, the number of colloidal particles can be counted. You can count it because bright stars, just like stars in the sky, na? So, of course, you cannot count the stars in the sky, but here you can count it because a beaker is there, but you are passing the light through it, and you are observing it under a microscope. You will see some particles will be shining there. That is nothing but the colloidal particles. We can say that clear, and the light will get scattered. It will get dispersed. We can say that. So, knowing the volume of the solution, the number of particles per unit volume also can be determined. Suppose you have taken 1 liter solution or 2 liter solution, you can count it, that how many particles are shining. So this further, listen carefully, this further helps to find out the average mass of the particle, which we have noted from the ultra microscope. Now we do not see the actual particles here, mind it. We do not see the actual particle. What I said you will see the stars, like the light which is scattering, the star-like object which is nothing but shining. Thus, ultra microscope, it not only gives the information about the size and shape of the particles, it also confirms the heterogeneous nature of the colloidal solution. Because what I said you in the beginning itself, I said in case of true solution, the light passes through simply. Alright, because it is transparent, the light passes through simply without getting any deviation. But here it gets deviated, it gets scattered. And if you see it, observe it under a microscope, then you can see this lighted particles. You can see it, alright, which is being floating there, which is being moving there, alright. By the help of the Brownian motion, it is being striking. One particle is striking another, other is striking another, and you will see it is what you can say a zigzag movement. You can see it, alright, by the help of microscope. Mind it, you have to see it. So that is the importance of the Tyndall effect, and this much I want to say you, that Tyndall effect, when you do the Tyndall effect, you see this particular thing in colloidal solution. The most important thing I said you, that it confirms the heterogeneous nature of the colloidal solution. That's very, very important. Now, next is, if you see the electrical properties of the colloidal solution, the stability of the colloidal solution is due to the fact that the colloidal particles in the solution, in the colloidal solutions, are electrically charged. The stability depends upon that only. As it is charged, so it is, what you can say, stable. The particles therefore repel one another and do not come closer to each other to form a large non-colloidal particle, so that it will get suspended. They are repelling. The charge which is present in the particles, due to which they repel one another. Suppose if they would have not repelled, they would have come closer to each other. They would have formed a big mass and they would have settled down as suspended particles. But this is not happening. So colloidal particles either carry positive or negative charge. All the dispersed particle in colloidal solution carry the same charge, while the dispersion medium has an equal and opposite charge present in it. Alright, an equal and opposite charge which is being present in it. We can say that. Now, next is, the question comes here, where from the charge appears on the colloidal particles. From where we are getting this particular charge? What is the origin of this electrically charge on colloidal particles? So there are various theories are given for it. One theory is that that is the electron capture by particles from air, and during what you can say the Bradig's arc method, you can see that is the particles it captures from the air. In the Bradig's arc method, what you are doing, you are taking, that is nothing but a solvent which is called the dispersion medium, and you are taking, there is two metal electrodes, you are passing electric current through it, and when it becomes hot, you immersed in a particular solvent. Let us say you have taken two gold electrodes. When it becomes hot, you immerse in water. You will see an electric arc is being produced. I have discussed with you. So there what is saying that electron capture. So when you are heating this, when you are passing electric current, when the electrode gets heated, some air, what you can say, surrounding it. Of course, air is a poor conductor of electricity, mind it. It gets surrounding that particular one, very near to it. Got it? It gets what you can say charged. So due to that also you can say that is some charge appear on the colloidal particles. It is being believed. Okay, this is one theory, that when you are charging the electrical rods, the metal rods, then the air which is surrounding it, very small amount of it, it's not a large amount, a very small amount of it gets charged. Now that depends upon also the voltage which you are passing through it. Suppose if it is low voltage, no question about it. But if it is high voltage, then only a small amount of air it gets charged. Now all these things you have studied in class 11 in atomic structure, in cathode ray experiment. When the pressure will be very, very low, then only it will be possible. Otherwise not, because air is a poor conductor of electricity. So this theory, it's not so valid, we can say that. Now frictional electricity caused by the mutual rubbing of the colloidal particles with molecules of the dispersion medium. Now this is quite convincing, that what happens is that when the dispersion medium and the dispersed phase, they collide with one another. So due to the mutual rubbing of the colloidal particles, so some charges appears, we can say that some charges appears in it. So that is another theory. It is being that is proved forward, it is being brought forward. Now dissociation of the molecules followed by the aggregation of ions. Now I have read it in micelles, where the aggregation of the ions is taking place. Alright. Now the soap solution. Now in case of soap, I am going to discuss later on about it. It gets dissociated from Na plus ions and have a tendency to aggregate into a cluster carrying negative charge. Alright. Its aggregates to carry a negative charge. I will show you. That is the what you can say the this is the soap solution. You can see the negative and the positive charge is being present here. That is here you can see the COO minus. This is soap molecule. You can see fatty acid chain is there. COO minus is a negative charge and Na plus ion is a positive charge. So in this way, what you find is that Na plus and CO minus, that is oppositely charged, are being developed. Now the particles of a dye have a tendency, dye means color, got it? So which is present in the clothes, have a tendency to dissociate to form aggregate carrying positive and negative charges depending upon its composition. Got it? So when you are putting soap upon the clothes, so these particles or the color, they also are having opposite charges, so they aggregate and they form clusters. Not big clusters, so that it will settle down. No. And hence they carry positive or negative charges depending upon its composition. We can say that. So this is another theory that is being put forward. So in this way, so many theories are being put forward regarding this what you can say the colloidal solution. We can say that. That where from the origin of the charge takes place in the colloidal solution. So now out of the various theories which I discussed with you, now one is very convincing, is that out of the various theories of the origin of the charge which I have discussed with you, now preferential adsorption of ions is considered as a best explanation. Now what is preferential adsorption of ions? Suppose you will take an ionic colloid, adsorbs ions common to its own lattice during the preparation of the colloidal solution. Now you must not be following. Let me give an example to you. Let us take if colloidal solution of AgI you want to prepare it. What you need to do? You will take potassium iodide solution and you will add it to silver nitrate solution. Simple. Potassium iodide, silver nitrate. Alright, it is what is being forming, that is nothing but double decomposition reaction takes place and it forms potassium nitrate and silver iodide. Correct? Now, so what is happening? Now listen here carefully. If we want to prepare colloidal solution of AgI, then you will add potassium iodide solution to AgNO3 till Ki is in excess, little bit excess. That means you want to prepare a saturated solution. Now iodide ions will be adsorbed on the surface of AgI. You have taken Ki in excess. So that Ki dissociates into K plus I minus, and I minus ion will be adsorbed on the surface of AgI particles, thereby giving them a negative charge. Alright, I minus, which is adsorbed on the surface of silver iodide. On the other hand, if colloidal solution of AgI is prepared by AgNO3 solution to Ki solution till AgNO3 in excess, in the previous case I have taken Ki in excess. Now suppose you are preparing same AgNO3 plus Ki, but you are adding silver nitrate in excess. You may also ask that suppose if I take silver nitrate in excess, what will happen? So very simple, what will happen? Ag plus ions will be adsorbed, thereby giving positive charge to the colloidal particles. If you are taking Ki excess, then iodide ions will be adsorbed on the surface of AgI. If you are taking silver nitrate excess, then Ag plus ions will be adsorbed on the surface of AgI, giving a positive charge, we can say that. So in either case, whether you take potassium iodide excess or AgNO3 excess, means a saturated solution if you take it, in either case the left out ions will remain in the dispersion medium. Left out ion means if you have taken Ki, then K plus ion is left out. If you have taken silver nitrate excess, then NO3 ion is left out now, because Ag plus ion is being adsorbed. Got it? Thereby giving equal and opposite charge to the dispersion medium. You got in the dispersed phase AgI and I minus. So what you can say, K plus ion is left out in the dispersion medium. If you are taking AgNO3 in excess, then Ag plus is adsorbed on the surface of AgI. So you get NO3 ions in the dispersion medium. In this way. Suppose you can take ferric chloride also. With ferric, when it's added to sodium hydroxide, you will get ferric hydroxide. Got it? So in this way, any examples you can take it and you can explain it. Got it? So this is quite convincing, this particular one. It is quite convincing, this one is. That is, when one type of ions of the electrolyte are adsorbed on the surface of the colloidal particles, it forms a fixed layer. That is, I minus ions, it forms a fixed layer, or Ag plus ions forms a fixed layer. It attracts the counter ions from the medium, forming a second layer which is mobile. Of course, it is I minus is going to absorb the K, it is going to pull the K plus ion, but K plus ion will be mobile. It will be moving throughout the dispersion medium. Got it? So that forms a diffuse layer. I minus forms a fixed layer over the AgI, but K plus ion will form a diffuse layer. Similarly, in case of AgNO3, Ag plus ion will form a fixed layer over AgI, but NO3 minus ion will form a diffuse layer. I hope you are getting in this particular one. So double layer of opposite charges thus formed is called Helmholtz electrical double layer. This is known as. As a result, a difference in potential exists between the fixed layer and the diffuse layer. The fixed layer is there on the adsorbed surface and the diffuse layer is there on the dispersion medium. So a difference in potential, definitely one is positive, another is negative, opposite charges are there. No? So a difference in potential exists, and remember it, listen carefully. This potential difference is known as electrokinetic potential or zeta potential. Zeta, Z-E-T-A, zeta potential it is known as. Got it? So the double layer of opposite charges thus formed is called Helmholtz electrical double layer. Got it? One is fixed layer, other is a diffuse layer. Already I said you. As a result of difference of this potential exists between the fixed layer and the diffuse layer, and this potential is known as electrokinetic potential or zeta potential, it is said to be as. I hope you got it, the origin, and I hope you got it, what is electrokinetic potential and the adsorption, what you can say, theory, that is preferential adsorption of ions from the solution. I hope you got it. In simple words, I've explained you. Now, next, coming to the next, what you can see in your screen, Hardy-Schulze law. Now, Hardy-Schulze law, before that, the last class you have read it about coagulation, flocculation, coagulating ion, a flocculating ion. I have told you about it. I have told you also, the smaller the coagulation value of the electrolyte, greater is its coagulating power or precipitating power. Smaller the coagulating value of an electrolyte. Now that is what is being given in the Hardy-Schulze law. So the Hardy-Schulze law has got 2 points basically. Got it? It has got 2 points basically. You may write it down, the Hardy-Schulze law. The main 2 points which are stated as follows. That is, the effective ions of the electrolyte in bringing about coagulation are those which carry charge opposite to that of the colloidal particles. These ions are called coagulating ions or flocculating ions. Again I repeat, the effective ions of the electrolyte in bringing about coagulation are those which carry charge opposite to that of the colloidal particles. If it is negative, then it will be positive charge. If it is positive, then it will be negative charge. These ions are called coagulating ions or flocculating ions. Now second point is much more important. Greater is the valency of the coagulating or the flocculating ion, greater is its power to bring about coagulation. Greater is the valency. Suppose you are having Na plus, Ca2 plus, Al3 plus. So Al3 plus will be having large coagulating power to bring about coagulation than Ca2 plus and Na plus. Got it? So greater is the valency of the coagulating or the flocculating ion, greater is its power to bring about coagulation. Just now explained with an example. You can see it on the screen also, it is being there. Alright, you are having AlCl3, BaCl2, NaCl solution, and Al3 plus, that is AlCl3 solution, will bring about coagulation easily compared to BaCl2 and NaCl, so to say. Similarly, in case of negative charge also same thing. Suppose if you are having that is ferrocyanide FeCN6 minus ions and phosphate ions, sulfate ions and chloride ions, which will bring about coagulation faster. That is FeCN6 minus, the ferrocyanide ion, we can say that. Clear? So higher is the charge, higher is the coagulating power, we can say that. Alright? Higher is the charge, higher is the coagulating power, we can say. So Hardy-Schulze law, it tells us that the quantity of the electrolyte which is required to coagulate a definite amount of colloidal solution depends upon the valency of the coagulating ion. It depends upon the valency that it was observed. That if you are adding aluminum chloride to coagulate, and if you are adding barium chloride to coagulate, so aluminum chloride will coagulate more than that of the barium chloride because valency is more. So you may require small amount of aluminum chloride to coagulate, to precipitate, we can say that. Clear? Got it? That is what the Hardy-Schulze law, the quantity of the electrolyte which is required to coagulate a definite amount of colloidal solution, it depends upon the valency of the coagulating ion. That is what I said you. That is what the Hardy-Schulze law say. So based upon that, we can say, we can have a formula: coagulating power of the electrolyte 1 by coagulating power of the electrolyte 2. Let us say aluminum chloride by barium chloride is equal to coagulating value of the electrolyte 2 by coagulating value of the electrolyte 1. Again I repeat, coagulating power of electrolyte 1 by coagulating power of electrolyte 2 is equal to coagulating value of electrolyte 2 by what you can say coagulating value of electrolyte 1. Now you must be thinking, coagulation value, what is this? That will be given to you. It will be given to you. For example, I remember it, and for that reason I am saying you. For sodium chloride it will be 52. For magnesium chloride it is 0.72, in this way. That value will be given to you. Just you need to put the value, whatever the electrolyte is given, and you will do it accordingly. Got it? Coagulating power, coagulating value you will be given, means 3 things will be given to you. The 4th one you need to find it out. That's it, what I want to say. Got it? In the formula. So in this way. So you understood what I said? That in case of positively charged, more is the charge, and in case of negative charge also more is the charge. Alright. So if more is the charge means valencies, then more is the higher is the coagulation power, we can say that. Alright. So in electrophoresis, the particles of the dispersed phase moves towards oppositely charged electrode and gets neutralized. If the process is continued for sufficient time, these neutral particles unite and grow in size and it settle down, we can say that. Alright, clear? We have already discussed this about this. Now next is, if you compare the coagulation of lyophobic and lyophilic colloids, then lyophobic soles are less stable and hence more easily coagulated. Listen carefully, lyophobic, liquid hating alright, are more easily coagulated than lyophilic colloid. This is because the stability of the lyophilic soles is due to two factors. What is that? Lyophilic soles. Same charge on the colloidal particles and solvation of the colloidal particles, we can say that. And this thus to bring about coagulation, both these factors has to be removed, and this is done by adding electrolyte or by adding suitable solvent. Now coming to the electrolyte, by adding electrolyte, I said, understood what I said, the lyophobic are less stable than what you can say lyophilic colloids. This is because stability of the lyophilic colloids is due to two factors. What is stability of lyophilic colloids? That is, what are the factors? I said use the same charge on all the colloidal particles. That is, it will repel, it will not come, and then it will not coagulate, and solvation of the colloidal particles, it dissolves easily in the colloidal particles. So thus to, if you want to bring coagulation, thus to bring about coagulation, you have to remove this. You have to remove the same charge which is there, you have to remove this. You have to see that it does not get dissolved completely. So how it is being done? By adding electrolyte or by adding a suitable solvent, we can say that. Now that adding electrolyte, that factor I am coming to you now. Alright, so what is that? The first you can see the adding electrolyte, that is gold number. What is gold number? So gold number of a protective colloid is the minimum mass of it in milligrams, which must be added to 10 ml of a gold sol, so that no coagulation of the gold sol takes place. 1 ml of 10% NaCl solution is added to it. It is there in the screen, we can say that. The gold number of protective colloid is a minimum mass in milligrams which must be added to 10 ml of the gold sol, so that no coagulation of the gold sol takes place when 1 ml of 10% sodium chloride solution is rapidly added to it. Alright, so this is known as protection of colloids. Now you must be thinking, why should I protect the colloid? Because if you don't protect the lyophobic colloid, then it will coagulate. Just now you said it. It is less stable. Lyophobic colloids are less stable than lyophilic colloids. Then it will coagulate. Got it? Now to prevent that, we need to protect it. For example, I can give you a very simple example. Suppose ice creams. You have said the chocolate cover is there over the ice creams. The chocolate, you can say it is cover is there, the layer is there over the ice cream, the chocolate ice creams. The chocolate layer, what it does? It prevents the ice cream to melt. So that act as a protective colloid, the chocolate. Alright. Now for you it gives a good taste, of course, fine. But according to chemistry, that acts as a protective colloid. It does not allow the ice cream to melt, to coagulate, we can say that. Similarly, upon the cake you can see, we are putting the cream. The chocolate or the cream we are putting it. What it does not allow the cake to, what you can say, shrink or shrimp, we can say that. So that the carbon dioxide gas which is being trapped in the dough, which makes the cake soft, alright, that is being retained. Because if you are putting a layer of chocolate or the cream upon it, so carbon dioxide will be trapped in it, due to which the cake will be soft. Otherwise, if you don't put the layer, what will happen? The carbon dioxide slowly and slowly and slowly it will diffuse out. By the help of effusion, it will diffuse out, and hence the cake will become, what you can say, just like chapati, it is going to become after some time, we can say that. So to prevent the cake to become what you can say chapati or shrink in size, what we are doing? We are putting a layer of chocolate or the cream upon it. So that acts as a protective colloid. Understood now? What is the use of the protective colloids? That is the use of the protective colloids, we can say. So here also same thing. If you want to protect the gold sol, then we have to add, that is 10 ml of what you can say 1 ml of 10% sodium chloride solution, so that the gold sol does not coagulate, it does not precipitate. Now you will say, why it will not coagulate? Why if it coagulates and what will happen? See, gold sol, where it is used, tell me. It is being used as an electrolyte to what you can say that is what I should say, that is electroplate the silver articles. Basically the silver ornaments, if we want to plate with electroplate with gold, then we require the gold sol, we can say that. So hence the gold needs to be protected. Otherwise, suppose if the gold sol coagulates, and it is a loss, big loss for the industries. You know what is the cost of gold now. Understood? Clear? So that is known as the protective colloids. Under the protective colloids, we are adding electrolyte, which I just talked to you. Now this is that is nothing but a soap solution. See, The head of the soap is water loving and the tail of the soap is water hating. You can see it here, hydrophobic colloids, which I have discussed with you. All the soap particles, you can see the head and the tail, they come together and it forms a cluster which is called as micelles. Got it? You can see it here, all this particular one. And you can see the chain, that is hydrophilic. The chain is what? CO minus, and after that you are having CH2, 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 CH2. So this particular one is hydrophobic, the CH2 part, and that the one which is hydrophilic is nothing but is your water loving, that is your the head of the what you can say, the soap, we can see. Now next is, after that we are cleansing action of the soap. Already discussed with you. Just I gave you this particular diagram so that you should go through it. Got it? When you are adding the soap solution to the oil or grease, and what it happens, it is being discussed here. Got it? It pulls out the oil and grease, and that is micelles it forms, the cluster it forms, and hence it cleans the clothes accordingly. So soap decreases surface tension of water, making it better wetting agent. Soap converts greasy and oily dirt into micelles that become dispersed in water. Soap keeps the greasy muscles in suspension and prevents it from redepositing. Got it? So already it is being discussed with you that when you are adding this detergent or the soap to the dirt or the grease clothes, then what happens is that it pulls out the dirt and the grease, and it helps to coagulate it and precipitate it. Got it? And when you are adding water, what happens is that is being washed away with the water, because soap decreases surface tension of water and makes it a better wetting agent. Now this is a reaction which is given. Soap, how it is being formed, we can see it is being given. See, ethyl acetate reacts with water, it goes hydrolysis. You have read it in chemistry, what you can say, organic, it forms acetic acid and ethyl alcohol. This is known as hydrolysis of esters. Now this ester, when it reacts with, instead of water it reacts with NaOH, it forms sodium acetate and ethyl alcohol. If it reacts with water, it forms acetic acid and ethyl alcohol. But if it reacts with sodium hydroxide, means the first one is acidic hydrolysis, the second equation is basic hydrolysis. In the case of basic medium, we can say that. So it forms sodium acetate and ethyl alcohol. Now what you will be seeing is that is one way you can get it, the soap. Another method here you can see is that we have taken a triglycerides, that is animal fat, which I have discussed with you in what you can say, alcohol chapter. When it reacts with NaOH, it forms glycerol and soap is being produced, RCOONA, because soap is a sodium salt of higher fatty acids. It's a higher fatty acids. Higher means R value is either C17H35 or C15H33 or C15H31. That is, you can take stearic acid or oleic acid or palmitic acid. Got it? Clear? So this glycerides, where from we get it from the animal fat. When it reacts with NaOH in presence of water, it forms glycerol, and soap is formed as a byproduct, we can say that. Got it? Already I have discussed with you all these things. So it's being done, this particular one. Thank you very much.